working on the sheet here, I want to kind of talk about just briefly the big picture as to what we're going to be doing here for the next little bit. So let's suppose that we have some curve, right? And I'm just going to draw, some curve. It doesn't really matter. And let's say that A is here and B is someplace over there, right? So what we talked about last time was that this area we designate with that symbol, right? And if the curve or the shape is something that like it's a bunch of segments of straight lines, or maybe it's like a circle or something like that, then we could use some like rules from geometry and just kind of carve it up and then like figure out what the area was without too much trouble. Okay, but what about if it's not some shape that we know from geometry? Well, then we're kind of out of luck. Okay. Um, and so the idea is, what could we do in that will work in a more general situation where we don't necessarily have some nice geometry formula. Okay, so to answer the question, let's kind of take rewind the semester all the way back to when we started doing derivatives. Okay, how did we start talking about derivatives? We started by saying, well, let's pick 2 points and let's find the slope in between them. Okay, and then what did we do to those 2 points? We let them get closer and closer together. Okay, what was true about the slope of the line that connected those 2 points versus the slope of the tangent when those 2 points got closer and closer together? They became the same when the 2 points were on top of each other. Okay, so the idea was we made an approximation and then we did some sort of procedure that would make the approximation get better and better and better. Okay, and we did so with the derivative by saying, okay, let's say that you're at some, let me just sketch kind of what I mean here. Let's say that you're at some point x. Well, then let's go over to some point x plus h, right? And then we computed the difference quotient, which would be the slope of the line that connects them. And then what did we throw in front of this to make it perfect? Yeah, we put a limit in front of it, right? So what that was doing was basically saying, okay, we've got this approximation, this difference quotient thing. It's an approximation for the slope of the tangent, but it's not going to be perfect unless h is 0, which it can't be, right? But if we let h become smaller and smaller and smaller, then this thing is going to approach some number or some value, and that thing is our derivative. Okay, and that's old hat at this point, right? So back to the problem at hand. What I want to do is I can't just magically find the area of this shape because it's not necessarily some geometric formula that I know. But what I could do is approximate the area of the shape and then figure out a way that I could always make my approximations get better and better. And so if I throw a limit in front, then we're good, right? Just basically play the same game we did with the derivative. Okay, so that begs the question then, how should we approximate this area in the first place? Well, what would be a way that we could do it? There's probably a bunch of ways, but what's maybe one idea? Well, what about if I had drawn this on graph paper? Could we just like count up the grids and get maybe a rough approximation? Yeah, it might take a while, but okay. So maybe a slightly better version of that, because that would be a little tedious, is what about if I just divide up this interval from A to B, and for the sake of the picture, I'll just chop it into 4 pieces. But let me then say, all right, here, 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 and here. Okay, and then let me pick a color. And let me say, okay, I'll do this one, I'll do this one, I'll do this one, and I'll do this one. And I'll compute the area of those 4 rectangles. Okay, is that a good estimate? You guess, right? It depends on what you mean by good. Okay, so the area of our rectangles, is it bigger or less than the true area? It's less than in this case, yeah. So this is the exact answer that we're trying to find. Okay, but let me change things a little bit. And does the orange look okay? Can you guys see it well? Okay. What about if I instead had picked these points and drawn my rectangles this way? What's true about the green area? Huh? It's more. All right, so if the green rectangles are too much and the orange rectangles are too little, this is sort of like a Goldilocks kind of thing, right? The true area is in between somewhere. Now, it may not be exactly halfway in between, but it's somewhere in between these two things, okay? So I've got here an overestimate and I've got an underestimate. Well, I drew here 4 rectangles for the sake of the picture, right? 4 green ones and 4 orange ones. And let's just take, say, either the orange or the green ones. Let's take the one on the far left here. We can see, for example, that the green one vastly overestimates the area because it includes this stuff, all this stuff that's above the curve, whereas the orange one vastly underestimates because there's a whole bunch of stuff that we should be including that's not inside the orange rectangle. Okay, so does that make sense then why one of them is too big and one of them is too small? Yeah, okay. So how could I improve this estimate? Yeah, let's do more rectangles, right? So here I drew 4 of them for the sake of the picture, but is there any reason, like mathematically, that I couldn't have done 8 or 16 or 1,000? No. Okay. So if I use more and more rectangles, equivalently, that's the same as saying using rectangles of tinier and tinier width, and I add up all of this stuff, then it's going to be perfect. Okay, so this is the idea behind what are called Riemann sums. Okay, and okay, all right. So let's actually get some numbers here. So looking at the graph on the sheets there, we've got the graph is repeated twice, okay, so it's the exact same function. And on the top graph, what I want you to do is draw the basically the ones that are the orange rectangles, and on the bottom, sorry, on the top one do the green rectangles, and on the bottom one do the orange rectangles. Okay, so actually draw them in, okay, and approximate the area because looking on the graph there, it actually has markings on the axes so that you can see what they are. Okay. All right. So take a second and do that, and then we'll come back together. All right. So put your hand on your head when you're ready for us to come together. Or actually, better yet, Yeah, I keep forgetting. Okay, so you guys remember the color code for the cups? Yellow means I'm working, leave me alone. Red means help. And green means I've got it. Of course. You're both working, need help, and are cool? Is that what that means? Uh, those are going to be the what we call our answers, right? So the top one, we're using rectangles whose y values are given by the left hand side of the rectangle, right? So you see how the green ones, their left hand edge is on the function. That one's left hand edge is on the function. So, and there are 4 of them. So we'll call that total L4. And then similarly for the right hand ones. All right. So what'd you guys get for the left-handed version? So this was the top one. So first off, do you guys agree that the area would actually be this formula? The width of each rectangle in this case was 1. That was convenient. And then what were the heights? 0.1, 0.5, 0.33, and 0.25, right? And so what does all that add up to? So what's 1 plus 0.5 plus a third and, well, here, let me just look and do it. 2.0833, like that. Does that look reasonable? Okay. What about on the left-hand side? Okay, so this is the bottom one. We would have 1 times a half plus 1 time, oops, times a third plus 1 times, dang it, 1 times a quarter plus 1 times a fifth. Okay, and so what did that one come out to be roughly? 1.28? Yeah, 3? Okay. Okay, so clearly one of those is too big and one of them's too small, right? Okay, in this case, how do we know in advance that the left-handed version was going to be an overestimate and the right-handed version is going to be an underestimate? What property does our function have? So looking at the graph of the original function, what property does it have? It's decreasing. Yeah. So because it's decreasing on the interval that we're working with, the left-handed version will actually be an overestimate, and the right-handed version will be an underestimate. If the function were increasing, those would flip-flop. Okay. And if the function is doing some weird squiggly stuff, then who the heck knows, right? So yeah, but what will be the case is one of them is going to overestimate and the other one is going to underestimate. And which one's which just depends on what the function is doing. Okay. All right. Now, I left some space here because I want to think about what we've really done. How did we compute the area of all these rectangles? Well, they're rectangles, right? So we just did base times height. Yes? Okay. And in this case, and often for convenience, what's true about the base? It was 1 in this case, but what maybe more generally, it was the same for all of the rectangles. Okay. And so I can actually write this in another kind of notation. And let me just write it and then we'll talk about it. How many of you guys remember that symbol from high school? It just means sum, right? Okay. And in this case, I'm going to do I equals 0 to 3, and it's going to be f of 1 plus I times delta x. Okay. Now, let's talk about what I mean here. What is delta x in our particular case? Change in x. How wide were our rectangles? In this particular case, they were 1. Okay, did they have to be 1? No. Okay, we just chose that for convenience. Okay, and so the thing that we're adding up here is really just the area of an individual rectangle, right? And what is the area of a rectangle? It's the width of it, which we're going to symbolize with delta x, times the height of it, which is going to be given by the value of the function at some place. Okay, now let's talk about the I equals 0 to 3 business. Okay, so if I equals 0 and I plug that in, I get f of 1, which was the first height of my rectangle, correct? Okay, if I equals 1, then I'd get f of 2. What's the height there? 1/2, and so on. Okay, now let's contrast that with the next one. Okay, because this one is going to look almost identical. Okay, so what's the only difference here? Yeah, we start at 1 and go up to 4 rather than starting at 0 and going up to 3. Okay, so, but in terms of what we actually are adding up, it's the same kind of thing. Width of a rectangle times height of that rectangle. What is the width? Well, that was a constant number that we just, like in this case, it was obvious. Okay, and what was the height? Well, that's given by whatever the function is, right? So that's why I have to have an f of something. Okay, now why do I have the 1 plus I inside the parentheses? Well, what's the leftmost x value in the problem that we're considering? Yeah, so looking at your graph, 1, right? We were trying to find the area between 1 and 4 of this contraption. I'm sorry, 1 and 5, okay? So what we were trying to find here was this, okay? And so both of those sums that we've written are approximations for the true value, this integral that we were after. Okay, does that kind of make sense? All right, so yeah, go ahead, Julius. The 3 and the 4. Okay, good question. How many rectangles did I do? In both cases, 4. Okay, so if I start at 0, 0, 1, 2, 3, that counted 4 things. Or 1, 2, 3, 4, that also counted 4 things. So the reason it was 0 to 3 or 1 to 4, it needed to have a total of 4 values. Okay. Now, Julius, I'm going to make an analogy for you that may not make sense to everybody else. This sum is basically a for loop, right? And in Python, right, when you do a for loop, you can do for I in range 0 to something or 1 to something. It's just which way do you start counting. You can count in either way, and geometrically, one of these corresponds to left-handed versions and the other to right. But we're still counting a total of 4 things in either case. Okay, does that kind of make sense? Yeah. So how many of you guys have done any computer programming before? The idea of a for loop, right? So the sigma notation is kind of a math version of a for loop where you just add every time. Okay. Anyway, okay. So we agree both of these approximations are pretty crappy, right? Because the correct answer should be like 1.6-ish. Okay, and we'll see why that's the correct answer in a few days. But for now, right, we just know that's an approximation. How can we make the approximation better? More rectangles. Okay, if we're going to do more rectangles, then that means more arithmetic. Okay, sorry. But, so what we want to do is basically take these two notations. Okay, which one did I use green? The big one. So the green one is this one, and the orange one was that one. Okay. We want to kind of give a slightly more general version here that allows us to deal with more rectangles. Okay. And in this case, I did it with n of them, or sorry, 4 of them. And that was partly selected because it makes the picture drawing pretty easy. Okay. But there's no mathematical reason why it had to be exactly 4. Okay. So does that sound okay? All right. So here's the idea. Okay. So let me start with 2 assumptions. We're going to use n rectangles, each of equal width. Okay? 2, we want to find this. Okay, so first thing, how wide should each rectangle be? So I want to write a formula for this that depends on everything that I've got in play. Almost. Okay, so that would be like the number of rectangles. Okay, but the width of them is going to be this. So if I'm going from A to B, what's the total width that I'm dividing up? B minus A, whatever that length is. Okay, and if I'm going to divide that into n pieces, then how about I divide it into n pieces? Yeah, okay. So the width of each of these contraptions is going to be B minus A over n. And for shorthand, we'll just refer to that as delta x. Okay, is that okay? Okay, so then I have two versions that we could do, because I could do the left-handed version and I could do the right-handed version. Okay, and like we saw with the particular example we did a minute ago, okay, this is where you have to kind of use your noodle on doing counting problems, right? How many things are there if you start counting at 0 and you stop at n minus 1? There are a total of n things. Okay, so maybe another way to think about this is if I have 10 feet of fence and I have a post every foot, how many posts are there? There's actually 11, not 10. Does that make sense? Okay, so that's why it's 0 to n minus 1 or 1 to n, because I need a total of n things in either case. The question is just, am I starting at 0, which was the left-handed version, or am I starting at 1, which is the right-handed version? Okay, does that make sense? All right, so those are just the sigma parts, but what do we actually need to add up in both cases? Times something, right? So what were we adding up? We were adding up areas of rectangles, yes? Okay, so let's add up areas of rectangles. So what is the area of a rectangle? It's the height times the width. Okay, and so the height is given by the function, so I'll put f of, and then I'm going to leave a blank so I can fill that in later. And what's the width of each one given by? Delta x. Okay, which was the number that we just computed a moment ago. That's the b minus a over n thing. Okay, so are we good with that? So now the question is, what goes inside the parentheses? Riemann. It'll be a little different than what we had a minute ago, so let me just write it. Okay, so that's a plus I times delta x. Okay, good question. So, in essentially what I want to do is my x values are going to be a starting value plus some offset, right? So look at the graph. What was your starting value for your x on the example that we just did? In both cases, it was 1, right? Because that was just the particular graph that we looked at. Okay. And so the x value that I want to plug into my function is going to be 1 plus something, right? And the something is going to get bigger and bigger as I move to the right. Okay, does that make sense? Okay, but each interval that I move over to the right was how wide? It was delta x wide, right? And that just happened to be 1 in our example. But I counted 1 rectangle over, 2 rectangles over, 3 rectangles, and I is the thing that's counting them, right? So for the left-handed version, my very first x value that I plugged in was 1 plus 0 times delta x. Okay, what was delta x in that case? 1. So my first rectangle in the left-handed version was 1 plus, well, nothing. So it'd be 1 plus 0 times 1, right? And so I plugged in f of 1. And what was f of 1 in our example there? It happened to be exactly equal to 1 because our function was nice. Okay, so that's why it is what it is. So I'm thinking, okay, I'm going to start at some place, and then I'm going to be, okay, I'm 1 rectangle over, I'm 2 rectangles over, I'm 3 rectangles over, I'm 75 rectangles over, I'm however many rectangles over, and the number of rectangles or units to the right that I am is some number between either 0 and n minus 1 for the left-handed version, or 1 to n for the right-handed version. Okay, that's all it's doing. I know this probably looks like it's Greek, and well, at least 2 letters are Greek. Uh, so, and I know it's 8 in the morning, and this is technical. Okay, yeah, okay. So that's the big picture here, right? Okay, so let's do. Let me maybe say one other thing. Did we have to use the rectangles all being the same width? We didn't have to. It would be way more complicated. Oh, yeah. Yeah. Okay. Okay. But it's not as easy to write down. So, that said, it's a nice assumption to choose the fact that all the rectangles are of equal width, right? That really will make our lives a lot easier. Okay. And so we will make that assumption. They don't have to be, strictly speaking, but that's much easier to deal with. Okay. And the second thing is, if I think about what's the relationship between these sums, right? These sums are approximations of something, right? So each of these is squiggly equal to this, okay? So squiggly equal, right, means that it's approximate, but it's not perfectly equal. Yeah. All right, so each of those things are squiggly equals. And what did we say happens if you use more rectangles? You get closer. So what happens if you use even more rectangles? You get closer. So how do I make this perfect? More and more and more and more and more rectangles. And how do we do that mathematically? We take a limit. Okay, so what I'm going to say here is that this limit, or the limit of the right-hand version, either one, is going to, well, I don't need to use the arrow here. It's going to equal this. Okay, so if I take either my right-handed or left-handed Riemann sums, okay, and I take the limit as the number of rectangles goes off to infinity, then I have defined the definite integral. Well, bam. Okay. And this maybe clues you in as to where this dx thing came from. Because stare at those two things that are next to each other. Right? We got a function, f of something, times a width. Right? So the delta x kind of becomes the dx. Okay, does that notation kind of make some sense? We? No. Okay, so sort of two questions that we want to answer. We've defined what this thing is, okay? And in certain cases, like if I pick a particular function, we can actually work out what the sum and then its limit is without too much trouble. Okay, I'll do an example of that. But doing it this way is not practical. So there's got to hopefully be another way, okay? And the way to sort of think about this is when we started doing the derivative, right? I had you guys, well, we had to do this. We started with the definition of the derivative, right? Limit as h goes to 0 of the difference quotient. And then we took a function like x squared. And we took the derivative and we went through that long limit computation. You guys all hated it because it was long and nasty and there was algebra. And eventually, what did you get out the other side? 2x, right? Derivative of x squared is 2x. And you were like, surely there's got to be a faster way to do this because x squared is a pretty simple function. What about if we have some really complicated function? Are we just going to be doing these limits all day long? And I said, be careful what you wish for because you just might get it. And then what happened? The product rule, the quotient rule, and the chain rule walked in the door. And you're like, whoa, 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 whoa. Okay. You take, yeah, exactly. No takesies, backsies. Okay. Okay. But point being, we had the definition and we were able to work things out, but it wasn't practical to do that for lots of different functions. So maybe there's some sort of shortcut. There will be, okay, which is what we'll continue discussing. But in the meantime, for right this instant, we're just, all we have is the definition, okay? So there are two things that we can do with this definition. One would be to do the approximation game like we did with the rectangles, okay? And two would be to actually sit down and do this limit, okay? And the sitting down and doing this limit is what we'll start with first thing on Friday, because I want to do some other stuff in advance of that, okay? Okay, so let's kind of flash back just a moment to where we started today, which was drawing these rectangles, but drawing a specific number of them just to get an approximation. Okay, so let's go back to what were the approximations we got for when we did 4 rectangles, left-hand version and right-hand version. We got 2 point something and, okay, and I said that the correct answer was like 1.6-ish. Okay, and I know what that is because of forbidden knowledge, right? Because I know the shortcuts. Okay, you guys would agree that our estimate's pretty crappy, right? We're pretty far off. Okay, so how can we make our estimate better? Average it. That's a pretty good idea. Okay, so if I average those two numbers, what do you get? Okay, which is a lot better than what we started with, right? So if you average the left-hand and the right-hand methods, you have to work out both of them in advance, obviously, so that you know what numbers to average, okay? But you end up with 1.6, what was it, 1.68? 1.63. 683, okay, 1.683. And the correct answer was like 1.60 something. So it's still not perfect, but would you guys agree it's a hell of a lot better than what we started with? Okay. Yeah, now why did that estimation get so much better when we just averaged two of them? Yeah, because if we looked back at the picture, so let me go back up here, right? We saw that the green ones kind of way overdid it, and the orange ones way underdid it. And so maybe there's something in between that's kind of just right. Does that kind of make sense? Okay, now if I average, so let me just take this very first rectangle, the green one and the orange one. If I average those two things, how could I think about what I've just done geometrically? There's two ways. One of them, let me get a blue. What I've done, oh, well, let me try that again. Let's actually use the fancy tool here. There we go. I know, isn't an iPad great? Okay, so by averaging them, what I've actually done is split the difference between them, which is the amount that's above the orange but below the green. It looks like a square here, but it's a rectangle of some sort, right? I basically just split that difference in half. Okay, and geometrically, I could think about either having a rectangle that was the average of the heights, or I could think about connecting those 2 points with a straight line. And it's kind of like if you have a grilled cheese sandwich, which way do you cut it? In half. How many of you guys do the triangles? Okay, how many of you guys do the rectangles where you cut it down the middle? Okay, you two need to leave. Okay. Right, but either way is a perfectly acceptable. Well, no, it's not, right? Okay, the rectangle, you people are, you just eat it. Okay, well, fair enough, right? But point being, you could cut it either way. And strictly speaking, either one is acceptable. Okay. So it's sort of the same thing here, but I'm going to choose to cut it into the triangle way. Okay. And the reason is because what is true then about the endpoints of my blue segment? Those are endpoints that I was already dealing with, right? And so that's nice. Okay. And if I could do that for the very first rectangle, could I keep this game up for the other ones? Yeah, okay. So what shape am I dealing with in this case? I'm dealing with, let me sort of highlight it. here, 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 and here. What shape is the blue thing? It is a trapezoid. Okay, so if you average the left and the right-hand methods, you get what we call the trapezoid method, okay, or the trapezoid rule. And is the trapezoid rule more accurate than the left or the right-handed version? Yes, definitely. Okay. But there's a downside. It's more work, right? Because if I just got it by averaging the left and the right-hand methods, well, I need to know what the left and the right-hand methods give me before I can do anything, right? I have to know those numbers. Okay, so point being, you have to know the left and the right-hand versions, okay, or use your noodle and tweak up those formulas a bit in order to even compute this thing in the first place. Okay, so this is sort of a rule, if you will, that is true about numerical stuff. The more accurate you want your answer, the more work you're going to have to do to get it. Okay, and so if you're okay with a kind of crude answer, then you can get away with a easier computation. Okay, but you always have that trade-off. You want a better answer, you're going to do more work. And where you are on the continuum of laziness depends on what you're trying to do, right? If you're trying to build a space shuttle, you had damn well better get it right, okay? Whereas if you're doing calculus homework, does it really matter if you're off by a tenth of a decimal point or something? Probably not. Okay, nobody's going to die anyway, right? But it could be the case that in real engineering and stuff that does actually matter. Okay, so there's the trapezoid rule. There's another rule, okay, called the midpoint rule. And for that one, what we do is instead of using the left and the right hand edges, I use the midpoints to determine the height. I still use rectangles, but I make their height dependent on not where the function is on the left or the right, but rather where it is in the middle. Okay, that is distinct from the trapezoid rule because it depends, basically I'm averaging at two different places. Do I average the x's before I plug them into the function, or do I average the values that come out of the function? If I average the values that come out of the function, that's the trapezoid rule. If I average before I plug into the function, that's called the midpoint rule. And just looking at the picture, would you guess that the midpoint and the trapezoid rule both are going to be pretty accurate, but they're not going to be equal? Probably. Does that seem reasonable? No? Okay. So the reason, because you're saying, why should it matter if I average on the beginning or at the end? Okay. And if the function is linear, then it wouldn't matter. But this function is not linear, right? Okay, so it's just going to depend on the function. Okay, now, the other thing we want to kind of think about here is, can we say which of these methods are bigger or smaller than the others and which are closer to the true values? Okay, first off, just by using our noodles, right, it's pretty clear that the midpoint and the trapezoid rules are better than the left and the right hand rules. That's for sure. Okay, but which one, so like looking at my trapezoid rule, is my trapezoid rule going to overestimate the situation or underestimate it? It's going to overestimate it. Why? Yeah, so you guys see there's a little bit of a gap between the blue line and the curve. It's a little hard to see in my picture because I kind of scribbled there, but you guys agree that that's true? Okay, now, why do I know that the curve is below the blue line? Well, in addition to this curve being decreasing, what else do I know about it? It is concave up, okay? Which means it sort of slows down as it's dropping if it's decreasing, okay? And so that blue line that connects the two dots, right, when I cut my grilled cheese sandwich, is a little bit above the function. and therefore it's going to overestimate. Okay, whereas the midpoint one, okay, which is that red line, is actually going to slightly underestimate for the same reason, actually, because the part of it that is this part here versus this part here, which one's bigger? The top one or the one on the left, either way you want to think about it, okay, is slightly bigger than the little wedge over on the right, okay? And so the top one, the midpoint rule excludes, but the bottom one, the midpoint rule includes, okay? So, conclusion, in this case, the midpoint rule would actually be a slight underestimate. Midpoint versus trapezoid, that actually depends on a few factors. In general, if memory serves I have to think about this for a second. If memory serves, the trapezoid rule is on average twice as good as the midpoint rule. I may have those backwards, but this actually is something, the errors of this, like how could you quantify what those errors are going to be in advance? That's actually a Calc 2 topic. And you spend like a week on it because there's a lot of stuff. Okay, so what we've basically discovered for this particular curve is the following. The integral, which I'll call I, the trapezoid rule we said was under or over? Over. And the left-hand rule was an over. And then the midpoint rule was under. Okay, for our particular curve, let me call I the true value. Okay, so that's the exact answer, whatever it is. Okay, I don't know what it is, but I do know that the left and the right hand rules are, one of them's too big, the other's too small. Yes. And I also know that the midpoint and the trapezoid rules, well, similar. One of them's a little too big, the other one's a little bit too small, and that the integral, the true value, is somewhere in between. Okay. Now, how did we produce the trapezoid rule? We averaged the left and the right hand rules. Okay, and the midpoint rule was basically averaging before you plug in rather than after. Okay, and in our particular case, okay, so the thing I drew in the box there, that's not always true. That's true for our particular example. Okay, and the reason that everything worked out the way it did there is because our function was concave up and decreasing. If we started changing that, then the order of these things might flip around. By and large, yes. Okay. Um, and there's, yeah, and that actually, by the way, that kind of thinking is what explains, or is the how you have to go thinking about the error stuff from a Calc 2 standpoint. Okay, so none of them are perfect unless your function just happens to be really, really easy. Okay, there is in fact a fifth rule for this, which is called Simpson's rule, and that one's really kind of complicated, but it would take me an hour to go through it. All right, so let me make sure that we've hit everything I wanted to hit today. Okay, we talked about yeah. Okay, so on the back there is another example that's maybe a little bit less contrived. Okay, so here you don't actually have a formula for the function. All you have is that table. Okay, and there are 4 graphs. So what I'd like you guys to do before you get here Friday, sketch the 4 versions on there, left, right, midpoint, and trapezoid, and compute those approximations. Sound good? All right. And then we'll start Friday with basically going through the limit definition of this and really, really having loads of fun with limits. Okay. And then next week you'll learn the shortcuts.